podcast. This is Mr. White.
Mr. Johnson.
And today we're going to talk about projectiles. Last time we talked about projectiles, but we talked about special angles. So what were our two special angles last time, Mr. Johnson?
0 degrees.
Right.
And 90 degrees.
And so just a brief summary. There we go. That's 0 degrees.
Mm-hmm.
That's 90 degrees.
Right.
Okay. Today we're going to talk about everything in between. So we're going to talk about launch angles that are less than 90 but greater than 0. So what do we know about projectiles, Mr. Johnson?
Well, when they go up, they got to come down.
So gravity still works.
I think it always works.
Yeah. You're giving away the secret.
Oh, sorry.
Gravity still works even on projectiles, okay? If I were to draw a projectile like this for greater than 0, less than 90, what does that kind of look like from a math class?
It looks like a curve.
It's a curve, all right? And specifically, it's parabolic.
Ooh.
Which means if we find the top, that the time on the way up and the time on the way down have to be what?
Equal.
Equal, because parabolas are symmetric. That's projectile motion. If we launch at anything other than 0 or 90, it's going to go up and it's going to fall.
Right.
And not only that, it will have some horizontal displacement.
Okay.
So that's different than we did in the fourth investigation. The other major thing we want to talk about is complementary launches. Okay? And so I guess let's start here. Let's start with the 45-degree launch.
That's a good one. Half a 90.
Half a 90. What's special about 45? Any thoughts about that? It's going to go far or not far?
That's going to go pretty far.
It's going to go far. Actually, 45 degrees goes farthest. And I wrote the word complementary up here. That's a word that comes and haunts us from our geometry past.
Oh,
yeah.
Here we go.
And so complementary angles added up to equal
90.
90 degrees. So the complement of 45 is
45.
45, meaning if I launch at this 45-degree angle, or if I launch at this 45-degree angle, they're both going to end up in the same spot.
Right.
The trick of this is complementary launches land. How about this? Let's not use that word. Complementary launches have the same range.
Now you're starting to talk projectile. Range.
Yeah, range. So range is delta x. So yeah, you can see that x there. Delta x, or how far it went from left to right.
Okay.
So let's change colors here. I meant for that to be blue. There we go. So I'm going to have a high launch angle. And let's say that the blue launch angle is 75 degrees. What do you immediately notice about the 75-degree launch with respect to the 45-degree launch?
Well, first off, it went higher.
It went higher, true.
And it actually landed a lot closer to where it launched.
Right. So it didn't go as far, and it went higher. Those are both true statements there. And so what's the complement of 75 degrees?
15.
15. So if we were to go with another color still, how about yellow? I can see blue and yellow.
Okay, I was just wondering. I know.
It's a big moment for me.
Like when you pulled out saying that's not blue, I'm like, oh, hey, all right.
The 15-degree launch angle.
It's pretty bright.
What do you notice about the 15 degrees?
Well, if you look at it, it doesn't go as high, but
Hmm.
it actually lands in the same spot as the 75.
Right. So just like 45 and 45, 75 and 15 have the same range, the same delta x. But let's do some comparison. So 75 degrees versus 15 degrees. Okay? They're going to have the same range. That's the only thing they're going to share in common.
Okay.
Okay? Everything else is going to be different. There's going to be a tiny flight time for 15 degrees.
Because it's not going as high.
Right. There's going to be a tiny vertical velocity, initial vertical velocity,
Okay.
because most of the motion is directed to the x, or right direction. Okay? That's important. The flight time for the bigger angle is much larger.
Right.
Most of the motion is directed up, so the initial vertical velocity is big. And since most of it is directed up, very little of it is directed to the right, so it's tiny. Okay? So when I'm using these arrows, this is not considered kosher math here. This is kind of made up Mr. White math. But the arrows symbolize for us, big, small, small, big, etc.
Right.
The only other thing that these guys share in common is gravity at negative 9.81 meters per second squared.
Why is it negative?
Well, why is it negative?
Well, I know why it's negative.
Do you think they know?
I would hope they would know.
I would think so. So gravity is this force that gives us weight, and specifically, if you were to let something go, what happens?
It begins to accelerate.
In which direction?
Downward direction.
Down. So the negative sign takes care of the fact that it's down towards the center of the Earth.
Okay. So what you're saying is, like, if, let's say I threw a ball at a 75-degree angle up in the air. As soon as I let go, it's accelerating in a negative because it's slowing down?
Yes.
Okay.
Right? It's accelerating downward even though it's going upward. And we spent a lot of time on that in Chapter 1, if you remember.
Okay.
Now, the other thing to remember is while I lied, I guess. While the components are big and small and big, the initial velocity is the same. Except when we break it apart into the horizontal and the vertical, that's where the variance takes place.
Right.
So initial velocity would be the same here for the angles. The range would be the same, and gravity is the same. But when we break velocity apart, different. And the flight time, different.
Okay.
Okay. The only other thing I suppose we should add here, same range means, we wrote this already, but delta x. This would mean a big, I don't know if I want to write delta y. How about a big y peak, meaning a high trajectory. This would have a low y peak. It doesn't get very high off the ground. So let's try and relate this to the investigation. You guys built data tables, and then we had you build models on the graph paper. You did not make graphs, you made models. Okay? And then we had you build a physical model with some string and a meter stick as we put all of this together. Okay? And what we calculated out was that if an object were just to fall, at first, the distance it travels is tiny. But it doesn't take long, and the distance grows quickly because it's accelerating due to gravity.
Right.
Right. And so actually, let's see, I want to color code this a little bit. I'm going to make these guys red. And if we were to take our object, okay, and we were to push any old object down or across a level table with no friction at a constant speed, it would cover the same distance in the same time interval. And so what we should be learning is that the motion of horizontal and the motion of vertical are going to happen regardless of what we do. There's nothing we can do about that. the motion is independent. An object doesn't know if gravity is acting on it. Gravity doesn't know if an object is moving to the side. So if you give it a push off the side of a table, it will fall and it will move to the right. And when you combine these moments in time, you get the flight of a projectile. And sure enough, this starts to look like what mathematical shape?
A parabola.
A parabola. And this would work even if we were to give it a launch angle. It's still going to be parabolic. We can still find the x and y positions of these things based on the time. And all we've got to do is match it up. So between the podcast and the data tables and the building of our paper and physical models, okay, this should start to become a little clearer and make some sense. Projectiles are hard.
Yes.
They're not easy to figure out because we're used to seeing things in just the x direction or in just the y, and here we are combining the two. I believe this wraps everything up. So signing off, this is Mr. White.
And Mr. Johnson.